Okay, so welcome everybody to the fifth lecture of the differential geometry lecture series. So till now, what we have learned is many different equivalent ways of defining second fundamental forms, and also last lecture we have learned how to calculate the recall. So if you have P in S is a point, then you had WPS. This is the Weingarten map. And from here, we have defined the Gaussian curvature, which was given by K is given by determinant of W. So let me call this as W. And then we have also seen the definition of mean curvature, H, which was the trace of right. This and then we saw many different ways how to compute the Gaussian and mean curvatures. And in terms of areas, finally we saw where we don't have to use actually the Weingarten map, or in other words the derivative maps. So this lecture we'll see another different way of how to compute the Gaussian curvature and also mean curvature, and finding out some more geometrical information of the surface. Okay, so let me start by recalling one lemma from linear algebra course actually. So let me say recall from a linear algebra course. So what I'm saying is, so suppose L is a self-adjoint linear map of vector space, or self-adjoint linear map, then what you can say is then V has a basis V1 to Vn of eigenvectors of L. So what I'm saying is, so if you have a self-adjoint linear map, then you have a base, you can find a basis V1 to Vn, let's say dimension of V is n, of eigenvectors of L. And moreover, not only the eigenvectors they are forming the basis, they have even nicer properties. So moreover, if Vi and Vj correspond to distinct eigenvalues, then they are orthogonal. So Vi and Vj, this is 0. So what I am saying is, essentially, in other words, we can find an orthonormal basis. Okay. So this is a basic fact from linear algebra, right? I hope everybody of you remember. I mean, in other words, what I'm saying is, if you have a real symmetric matrix, let's say some S, then you the matrix is diagonalizable. Or in other words, you can find some matrix P such that P S P transpose is diagonal matrix consisting of eigenvalues. Right? So why I am interested in this? Because if you remember from a previous lecture, when we define the second fundamental form, this operator, this Weingarten operator, this we actually saw that this is a self-adjoint and this is a linear map. So essentially, I am going to use this fact on the operator of this Weingarten. Okay. So let me continue with the proposition immediately. So proposition. So let P be a point in S, then there are scalars K1 and K2 and a basis T1 and T2 of tangent plane TPS such that W of T1 is given by Kappa 1 T1 and W of T2 is given by Kappa 2 T2. Okay, and moreover, if K1 is not equal to K2, then the inner product of T1 T2 is 0. Okay, so this is just immediate application of this fact from linear algebra, right? Because what I'm saying is I'm just using W is a linear map from TPS to TPS, and then essentially these are the eigenvectors and these K1 and K2 are the corresponding eigenvalues. So there is no proof needed. I mean, this is just immediate from here, and this allows me to give a definition. So this Kappa 1 and Kappa 2, they are called principal curvatures. Okay, and correspondingly the eigenvectors T1 and T2, they are called principal vectors. Okay, and since W is a self-adjoint linear map, I mean, via this proposition, essentially, we always have the existence of K1 and K2 and correspondingly T1 and T2. Okay. So, okay, so this gives us another notion of principal curvature. And what we will see is somehow this principal curvature can be also used to compute what are the other curvatures we have seen, Gaussian and mean curvatures, and another one was normal curvature. So we would see that this principal curvature, this actually give a very simplified way of determining both of these, like the Gaussian curvatures and also the normal curvatures. And finally, we'll see that this also helps us in determining many different nice geometric properties of a surface. So okay, so that's the first definition. And if you go back to this proposition, you would see or the fact from the lemma. So we always have this assumption if K1 is not equal to K2. So that's actually gives us a motivation to define the scenario where K1 is equal to K2. So let me define this. So P, the point in S, is called umblish if the eigenvalues are equal at P. Okay. Yeah, this is a very strange name actually. Umblish. I mean, this actually comes from a Latin word umblicus, which means novel. I mean, so it's actually kind of a description of a, let's say, local sphere, local property of how the sphere looks like locally. That's in Latin called umbilicus, and that's why it called umbilic. And why I'm saying this, you will understand maybe today at the last, or maybe tomorrow, that if you have a surface with all the points are umbilic, then that becomes a sphere. So somehow that gives the motivation of defining this as umbilic. So then immediately let me remark, if you have a point, if P in S is umbilic, then K1 is equal to K2, right? So what if you write down this, then what are you having? W of T1 is kappa T1, and W of T2 is kappa T2. So this implies what? W of T is kappa T if T is any linear combination of T1 and T2, right? Because just by the linearity property. So this means that this P is actually an umbilic point if and only if W is a scalar multiple of the identity map. And this implies then every tangent vector becomes a principal vector, right? Because every I mean, this W, if this is true for an umbilicial point, then of course for every tangent vector also becomes principal by just definition. So this is nice. So if you have a point which is umbilic, then every tangent vector is principal. Let's see if it is not an umbilic point. So if P in S is not umbilic, then also what do we have? By definition, T1 and T2, they correspond to they correspond to two different eigenvectors, which are the principal curvatures. But here, since I have assumed that this is not umbilic, then that forces us to have K1 is not equal to K2. But then let's see, let me go back to the definition here. Yeah, see, here we have, if K1 is not equal to K2, oh, sorry, yeah, if K1 is not equal to K2, then T1 T2 is orthogonal. So that's the exact thing I am saying. So then T1 T2 corresponding to K1 K2, and K1 is not equal to K2 because this is not umbilic, then they are orthogonal. So they are orthogonal. So essentially, by this remark, what we get as a corollary that if P in S a point, then there exists an orthonormal basis of the tangent plane TPS consisting of principal vectors. So what I'm saying is, so independent of the point being umbilic or not, you can always get a basis which consists of orthonormal basis, which consists of only principal vectors, which makes sense, right? I mean, that's not that unbelievable to believe. But this has a very nice corollary then, which allows us to compute the Gaussian and mean curvature in a very simple way. So that's the next proposition. So let's say if kappa 1 and kappa 2 are the principal curvatures of a surface at a point P, let's say, then the Gaussian curvature is given by just the product of these two, and the mean curvature is nothing but half of the sum of K1 plus K2. I mean, this you should see it, right? I mean, why this is happening? I mean, let me just give the proof. So what was the definition of K? K was determinant of this W, and H was half of trace of W. Now, what is determinant of W? Essentially, you write W in terms of a basis of TPS, and then you compute the determinant of the matrix associated to W. And now from the corollary, what we get is we already have an orthonormal basis which consists of principal vectors. So essentially what we can do is we use the basis of the principal vectors. And if we use the basis of principal vectors, then the matrix is given by K1, 0, K2. And then we are done, right? Because determinant of this matrix is this one, like this one, and half of trace is this one. So essentially, if you know the principal vectors, kappa 1 and kappa 2, then you know the Gaussian curvature, and you also know the mean curvature, which is a very simplified expression. Is it clear?
Yes, sir.
Perfect. Okay, so as I promised, so this gives us a nice expression of the Gaussian and mean curvature in terms of principal curvatures. Then the next thing what we'd see is a expression of normal curvature in terms of principal curvatures. So let's see how this is we are getting. So this was actually a theorem, or sometimes it's called Euler's theorem in the literature. So let gamma be a curve on an oriented surface S, and let kappa 1 and kappa 2 be the principal curvatures of a surface space sigma with non-zero principal vectors T1 and T2, then the normal curvature, which is given by kappa n, I mean, which is the notation is kappa n, is given by kappa n would be kappa 1 cos square theta plus kappa 2 sine square theta. So where theta is what? Theta is the angle between the cross product of T1 and gamma dot. So where theta is the oriented angle T1 gamma dot. Okay. So So the statement is essentially the normal curvature is given by k1 cos square theta plus k2 sin square theta. Okay, where theta, let me go through the proof and I will draw the picture also, then it will be even more clear. So let's start. So we have what we have that kappa 1 and kappa 2 are the eigen values corresponding to the eigen vectors t1 and t2. So essentially, by the above corollary, we can assume so t1, t2 can be assumed to the to an orthonormal. Sorry, any question? Okay. Yeah, so from the previous corollary, we can already see that T1, T2, this can be thought as an orthonormal basis of the tangent plane. And now let me just draw the picture. So here I take the T2 and here I take the T1 and here I take. So this one is T2, this one is T1, this one is the gamma dot, and that's the theta. This is what I have defined, right? T1 and gamma dot, the angle between this. And we can also assume that the angle between T1 and T2, this is plus pi by 2. How? Because if, I mean, possibly by you can have minus T2, so then you might have minus pi by 2. So but you can change that. I mean, you can replace that then T2 by minus T2 in the orthonormal basis, right? So possibly by replacing T2 and minus T2. So this also you can assume. So if this is the case, then okay, here I have space. So now let's see the Kn, the normal curvature. If you remember the previous lecture, this was nothing but given by the inner product of gamma dot and gamma dot. Okay. And now you write this gamma dot in terms of T1 and T2, and then you expand the inner product. So then this is nothing but cos square theta T1 T2 plus 2 sine theta cos theta. Sorry, it's not T1 T2, it's T1 T1, and this is T1 T2 and plus sine square theta T2 T2. Okay, so now we are actually quite close, because what is T1 T2? T1 T2 we have taken as an orthonormal basis. So what does that mean? That T1 and T1, this would be what?
T1,
Sorry?
T1, T2 is equal to 0.
Exactly.
T1,
So this whole term is 0.
To K1.
Perfect. Nice. So then this becomes immediately, you can see that K1 cos square theta plus this term actually vanishes. And this term is what? Then T2 and T2 is K2, right? Yeah, perfect. Yeah. So this is K2 sine square. That's exactly what we wanted to prove. See? Yeah. Okay. Perfect. So this gives us another way to compute the normal curvature actually in terms of K1 and K2. And this actually also gives us an immediate corollary, which also kind of a characterization of the normal curvature, which you would see in many literature also. So the principal curvatures at a point P in S, these are the maximum and minimum values of normal curvature of all curves on the surface which that pass through the point. So what I'm saying is the principal curvatures, they are essentially the the K1 and K2, if they are non-zero, let's say, they are the maximum and the minimum values of all the normal curvatures of all curves that pass through that point, which is a very nice geometric intuitive thing, right? And the proof is essentially just a corollary of the previous one, we will see immediately. And moreover, not only the eigenvalues essentially, what about the eigenvectors? So essentially the principal vectors, they are the tangent vectors of the curves, which gives this maximum and minimum. Because that's by definition, right? If the let's say maximum is given by kappa 1, then correspondingly you get a tangent vector T1, and that is also the principal vector. So that's exactly what I'm writing. So moreover, the principal vectors are the tangent vectors of the curves giving these maximum and minimum values. So this portion, moreover, it's kind of immediate. What we need to prove is this maximum and minimum values, but this will be, you would see immediately. This is also quite immediate. Let's see. So first of all, let's assume without loss of generality that kappa 1 is greater than kappa 2, because we are assuming kappa 1 is not equal to kappa 2. So this we can assume. Then the previous, this Euler's theorem, this gives you what? Kappa n, which is the normal curvature. This is nothing but kappa 1 cos squared theta plus kappa 2 sine squared theta. And now kappa 1 greater than kappa 2 means K1 minus K2 is positive. So I'll rewrite this equation in terms of kappa 1 minus kappa 1 minus kappa 2 sine squared theta. I just expand cos squared theta is 1 minus sine squared theta. And then clearly, now you see kappa n is lesser equal to kappa 1, right? Because this is positive and it is sine squared theta. So this whole thing is positive. So kappa n is lesser equal to kappa 1. This is immediate. And when does the equality holds? When this is
theta equal to 0.
0 or pi.
Oh, okay, pi.
Right? Yeah, that's one case and no. So exactly. So nice. So with equality, if and only if theta is 0 or pi, right? But if theta is 0 or pi, that means what? In other words, then the tangent vector gamma dot of gamma, this is essentially, it became parallel to T1. Right? By definition again, theta, if you take theta is 0 and that was the theta. Theta's definition was T1 and gamma dot, right? That's the angle. And similarly, you can also prove that kappa n let me share the screen again. Yeah, sorry. So where was I? That kappa n lesser equal to kappa 1, this we already saw. And now the other way, we will use the when kappa n is greater or equal to kappa 2. This is nothing, it's again similarly, right? You can just use sine square theta is 1 minus cos square theta and then use the other way. So this will be again quite easy to see, and with equality, if now gamma dot is parallel to T2. So this is essentially we are done, right? Because so here you are saying kappa 1 is attained from how you are getting as a maximum value, or here as a minimum value. So then we are done. So that's exactly the proof. And then similarly, let me just conclude. So if kappa 1 is equal to kappa 2, then kappa n is equal to kappa 1, and you get that every tangent vector to the surface is a principal vector. So this is being done. So let me read out the statement again. So this is quite nice geometrical intuition about the normal curvature and the principal, relating normal and principal curvature. So what we are saying is the principal curvatures, they are essentially the maximum and the minimum values of the normal curvature. And that's exactly what we proved, right? So the kappa n is lesser equal to kappa 1 and kappa 1 is greater equal to kappa 2, and the equality attains at some case. So those are the exactly values what we just saw in the statement of the corollary essentially. Okay, so this finishes the thing what I said, that the normal and normal curvature and the Gaussian and mean curvatures, they can be determined in terms of principal curvatures. So now the next question should be asked is, can we determine the principal curvatures explicitly? And of course we can. So in terms of first and second fundamental forms, what we have also seen in the every curvature calculation, right? So let's do this again. So kappa 1 and kappa 2, this also can be computed explicitly for a surface S, sigma UB a surface patch, with first and second fundamental form given by E du square plus 2F du dv plus G dv square. And the second fundamental form is given by L du square plus 2M du dv plus N dv square. And then we have also defined Fi as the symmetric matrix E, F, F, G, F, I for the second fundamental forms L, M, N. So help me with the matrix of W. This we have already computed. What was this in terms of these two matrices? Can you remember what was
If I inverse F
Fi?
topology?
Yeah, perfect. So this is, we are already in a very good shape, right? If we know the matrix of W, then what are the definitions of kappa 1 and kappa 2? These are essentially eigenvalues of this, and we know how to compute eigenvalues and eigenvectors from linear algebra, right? So kappa 1 and kappa 2, essentially they are roots of the equation determinant of Fi inverse Fii minus kappa I is 0. Yeah, that's the eigenvalues. And correspondingly, if T as, let's say, xi sigma u plus eta sigma v, any principal vector, then it is given by the solution of the equation Fi inverse Fii minus kappa I zeta eta 0, 0. Right? That's just the linear algebra. So these are the essentially eigenvalues of this one, and these are the eigenvectors corresponding to these eigenvalues. Okay. So this gives me, just let me write this down in a nice proposition way. So the proposition, the principal curvature are roots of the equation. You take the determinant of L minus kappa F, M minus kappa F, M minus kappa F, M minus kappa G. This is 0. And the principal vectors corresponding to the kappa 1 and kappa 2 are the tangent vectors T zeta P such that L minus kappa E, M minus kappa F, M minus kappa F, M minus kappa G. Oh, sorry. Sorry. 0. Okay. So what's the proof? I mean, proof is nothing but you just write Fi inverse Fii minus kappa I in terms of Fi inverse Fii minus kappa times Fi. And then you just write down the matrix, and then you get the determinant. I mean, you should have something here, but this is 0 automatically, right? So the roots are just, this is enough to have finding the roots for this one. So this is okay. So this is, I mean, this proposition is nothing but what we already saw here. That's determinant, that's the roots, those are the principal curvatures, and the principal vectors are just the solutions of the equation, this one, which corresponds to the corresponding eigenvectors. Okay, so this gives us the way to compute it. So let's compute for some examples. So let's say S square is unit sphere. So this we have already seen. We have compute E, F, and G. We have also computed L, M, and N. So then K1 and K2 essentially are roots of, now we put this all values. It's 1 minus kappa 0, 0, cos square theta minus kappa cos square theta, the determinant of this guy. So this is given by actually kappa 1 is equal to kappa 2, which is same as 1. So we essentially you would have repeated roots. So what you are finding out that the principal curvatures are equal, I mean, to each other at every point, and over the whole sphere, it's actually remains constant, which is expected, right? Because the changes of the curvature on the sphere, this we have seen at many different. I mean, the one valid objection one should actually make, I guess, here when I was before. Yeah, I mean, not before. I mean, when I was. Yeah, so for example here, so I said as a motivation that the Gaussian curvatures can have a simplified way as kappa 1, kappa 2, and also the mean curvature has this expression, and also the normal curvatures has this expression. But you should object that when I am computing the example, I'm actually using the first and second fundamental form. And then if we have these two, then automatically you can also compute directly the Gaussian and mean curvature. So it doesn't really make sense to have this one and then again going back, but it's like a somehow coherent of all the concepts, and these are related in some sense. So sometimes maybe this can be useful, sometimes maybe the explicit computations can be useful. It depends. Okay. So let me compute another example. Example 2. So here, let me take the unit cylinder actually. So let me take this, and here I'll take T2, sorry, T1, and here I'll take T2. So what I'm taking here, the surface is given by unit cylinder, given by the surface spread sigma UB is cos V sin V U. And then we have again computed E equal to 1, F equal to 0, G equal to 1. And this I'm not even asking anymore. These you have computed many times. It's just simple calculation. L equal to 0, M equal to 0, N equal to 1. This is nothing deep. I mean, you just compute it. So essentially, this gives the kappa are roots of the determinant 0 minus kappa, 0, 0, 1 minus kappa is 0. So this gives kappa equal to 0 or 1. Okay, and then correspondingly you get, so correspondingly, let's say if kappa is 1, so if K1 is 1, then T1 satisfy the equation minus 1, 0, 0, 0, psi 1, eta 1 as 0. So this would tell you that psi 1 is 0 and T1 is multiple of sigma V actually, which is nothing but minus sine V cos phi and 0. And similarly for kappa 2 equal to 0, you can also. So this is not that illuminating, but let me focus on this one first. So here you have a nice property that for every point at the surface, the principal curvatures are same and it remains constant. So what I'm saying is, remark that example 1, this proves that on a sphere. So another point, let me say this. So if kappa 1 is kappa 2, then all the points in the surface, which is the unit sphere in this case, then every point on the surface is an unbleached point, right? Because kappa 1 is equal to for any point. So that's exactly what we get, that example 1 proves that on a sphere, every point is unbleached. And you can, there is another surface actually. This is also true. This is also true for if you take S to be a plane. Why? Because then kappa is 0 everywhere, right? This you could see intuitively also, and you can compute directly also. But I mean, so what am I saying? That for a sphere, every point is unbleached, and for a plane, that's also true. Every point is an unbleached. The interesting thing is, this is also true in converse, and that's exactly the next proposition. And this starts actually the last phase of our lecture series, of my lecture series, that kind of classifying the surfaces using different kinds of curvature. So here I am going to first classify, so let S be a connected surface. And I assume that surface of which every point is unbleached. So what I'm saying, that at every point, the principal curvatures are same. K1 is equal to K2. So for this, we know already 2 examples. One is a sphere and one is a plane. The proposition says this is the, these are the only scenarios. So if you have a connected surface of which every point is an unbleached point, then S is actually an open subset of a plane or a sphere. Let me immediately remark, and then I will go to the proof of this. It's a very nice proof using all the things what we have used till now. So as I have always tried to motivate you using examples of curves, so let's see what was the analogous statement for curve. We had every let's say every plane curve. Every plane curve with constant curvature, which is the analog of our principal curvatures are same. This was actually part of a circle. And that's kind of a similar, that which we are having open subset of a plane or sphere. Okay. So now how should we prove this? Let's try to do this. I mean, so first of all, what do we know? Our assumption is every point is Amblish. So that means what? For every tangent vector T, we have W of T is kappa of T by definition of Amblish point, and where kappa is essentially the principal curvature. Now let sigma be a U to R3 be a surface patch where U is an open subset of R2. So once we have, then we this we have actually used many times. Take the canonical basis of the tangent vectors. Take D equal to sigma U and sigma V. Then we have seen that W of sigma U, this is nothing but minus NU. N is the unit normal vector, and W of sigma V is minus NV. This we have seen many times. I mean, let me see if we can find it here. Yeah, I don't think this here. Oh, here. Yeah. Yes, here. So this we have already seen. Yeah, exactly here. So W of sigma U is minus NU and W of sigma V is minus N. So this we have seen many times, and this I actually also I think used last time. These are standard tricks. So once you have this, then let's see what happened to. So this implies NU. This is minus kappa sigma U, because you can now use W of sigma U is kappa of sigma U from here, right? This is true. So this you can put as this, and then you are rewriting this. And similarly, then NV is minus kappa sigma V. Let me term this as star. So this implies, now you see, let's take kappa sigma U V is nothing but minus NUV. This now I can interchange minus NVU, which is nothing but kappa sigma VU. So what I'm saying, this means that kappa V sigma U is nothing but kappa U sigma V. But now again, let's see if you remember the regularity definition. If sigma is regular, then do you remember what was the property of sigma U and sigma V?
Sigma U and sigma V are linearly independent.
Perfect. So they are linearly independent, and now I have managed to find a non-trivial relation between this. So that means what? So this means kappa V and kappa U both are 0. And this means what? That kappa is actually
Constant.
Constant. Perfect. So now we have already reduced to the case that if every point is an Amblish point, then the surface on the surface, the kappa will be constant at every point. So now we have two cases actually. Case one, kappa is actually 0. Okay, so that's the first case. So if kappa is 0, that means what? So here now let's see what is the star is giving. Kappa is 0. That means what? NU is also 0 and NV is also 0. So this gives that NU is 0, which is also NV is 0. And this gives N is also constant. Okay. So this implies if you take N dot sigma and take the derivative with respect to U, this is N dot sigma U, this is also 0. And similarly, n dot sigma v, this is also 0. So this means n dot sigma is actually some constant, say c, and this implies that sigma u is nothing but it's an open subset of the plane given by v dot n is c. So essentially we get that if it is a zero principal curvature at every point, then the surface patch is actually included in the plane. Okay, nice. So the next case is what? Case 2 is kappa is non-zero. So how, let's see again, let me come to this point. I mean, let's consider this star again. So this nu and nv. So if you now so write this down, star is non-zero, then n is nothing but minus kappa sigma plus a for a some constant vector. This is just from definition, right? I mean, definition, I mean like from the star essentially, and then from the definition. And then this is nice because, sorry, this gives you, if you take the norm of the difference, so this is nothing but minus 1 by kappa n norm square, and n is unit normal, so this is nothing but 1 by kappa square. So see now what are you getting? That sigma from a center, its distance is always 1 over kappa square. That means what? That this is a surface patch of a sphere. So essentially this gives you that sigma u is essentially an open subset of a sphere with radius 1 over kappa at center 1 over kappa a. Okay, so essentially we are almost done if the surface has only one surface patch, because see what we have assumed. We have assumed that let sigma be a surface patch, but in general, S can have an atlas, right? I mean, like consisting of many surface patches. But from the previous argument, what we have obtained is for every surface patch, sigma of u is either contained in a plane or a sphere. So now you should realize that if, let's say, image of two patches, I mean, so if image of two patches intersect, then they must be part of the same plane or sphere, right? So then they must be part of the same plane or sphere. So then once you are covering the whole surface, then essentially we are done. Okay, so I mean, let me just in the last minute, so let's see how we went. So we assume that every point is an Amlish. That immediately gave us that the principal curvature at every point is constant. And then we took two cases. One is kappa is zero when it's a subset of a plane, and another case is kappa non-zero. Then it's a open subset of a sphere. And but this was only for a single patch, but since we know that it can be covered with many different patches to form an atlas, and for every intersection of two patches, then they if they intersect, then they must be part of the same plane or sphere. So essentially you can cover as a same plane or same sphere, and then you are done essentially. So this is kind of the it's the first in series I mean, tomorrow I will show you many different classifications where we will have different Gaussian curvatures or different principal curvatures and classifying surfaces. So essentially, you should, I mean, this you must have seen in many different areas of mathematics, right? Once you define some invariant, like here, curvatures are invariant of some surface. So invariant meaning what? That this carries some information of the surface. Then once you define some invariant, then you should be expecting that that invariant should be nice enough to classify some surface. So for example, here, we find a nice classification of a surface, and then tomorrow also I'll show you different results of how one should classify different kind of surface using different either principal curvatures or positive, negative, or different Gaussian curvatures. Okay, yeah, I'll stop. Sorry for 2 minutes over time. Yeah, please.